This is a production involving a number of different experts within the Knowledge Transfer Network. There's myself, I look after quantum technology. We have a huge quantum program in the UK, which is worth about 1 billion over 10 years. My colleague, Charlie Winkworth-Smith, has a network on neurotechnology, and my colleague, Gabriella, is representing the healthcare team within the Knowledge Transfer Network. This is the agenda. First off is going to be Professor Matt Brookes talking about magnetic sensors, followed by Carolyn O'Dwyer talking about a particular type of magnetometers. And then we're very pleased to have Professor Stefano Seri, a clinician, talking about how this will actually be used in the real clinical world. We will have a few minutes after each presentation for questions, and then we'll have a panel session to wrap up. If I could just ask you these few housekeeping details. Everybody will be muted during the presentations, except of course the presenters. Please use the Q&A box to post questions, which we will be monitoring, of course, through the talks, and we'll use that to feed the question session immediately after each talk, and then for the Q&A panel session at the end. You also have the chat box, but please just confine yourself to using that for technical issues rather than questions that you want the panel to see. So at this point, I will stop sharing my screen and I will hand over to Matt Brookes.
Okay, so I guess it's my job this morning to kick off and to explain a little bit about what we're doing, why we're trying to do brain imaging using magnetic sensors, and the types of things that we can that we can measure. So I think it's fair to say that understanding the human brain and the 86 billion neurons that are inside it is one of the major challenges for 21st century science. Why do we do it? Well, there are so many cases where people suffer with disorders of the brain. So for instance, 1 in 4 people will suffer from a mental health disorder at some point in their lifetime. But we actually know very little about the neural substrates that cause those disorders. Likewise, perhaps at the older end of the spectrum, in 2015, nearly 30 million people worldwide were suffering from Alzheimer's disease, and in an aging population where the average life expectancy is going up, we know that the prevalence of dementia is growing. At the other end of the spectrum, we know relatively little about how children's brains change as they grow up. And of course, if we don't understand how the healthy brain develops, we don't understand how that neurodevelopment goes wrong in kids who have profound difficulties. And I could go on and on. I know Stefano's going to talk later about epilepsy. Around 60 million people around the world suffer from epilepsy. It's extremely debilitating. But again, we don't fully grasp the brain networks that cause it. And we can go on schizophrenia, mild traumatic brain injury, and we can go on. And I think to summarize very briefly what I've already said, understanding the human brain and treating the many disorders that affects it is one of the biggest challenges that we're going to see in the next few decades. So it's a big challenge. What's the good news? Well, the good news is actually over the last, I don't know, maybe 20 or 30 years, we've seen the introduction of incredibly powerful scanners. The example I'm showing here is the MRI scanner, which can measure what the brain looks like in ever increasing detail. So at very high field MRI, we can get images of the brain at sub-millimeter resolution. And they've really been a fantastic way to try and understand and indeed to manage brain disorders. But most brain imaging techniques, MRI included, their primary role is to measure brain structure. So in other words, what the brain looks like. And that's That's great. See, you know, we can look for lumps and bumps, we can look for tumors, things like that. But in an awful lot of conditions, in many cases in mental health, in some cases in epilepsy, the brain looks essentially normal. And it's really very hard to spot anything. There are no holes in it or anything like that. It's not that brain structure has gone wrong, it's that something has gone wrong with brain function. The way in which these neurons fire is somehow going wrong. And so that means that in addition to the very powerful structural scanners like high field MRI or X-ray CT, we also need to develop machines that can measure what the brain actually does, that can measure the function within assemblies of neurons. So that brings me on to why we might want to do, why we might want magnetic sensors and why we might want to image the brain from a magnetic standpoint. So the idea of magnetoencephalography, or MEG, or MEG, is to measure the magnetic fields that exist outside the head that are generated by current flow through assemblies of neurons. So in just the same way that any electrical current generates magnetic fields, the neurons in your brain, as current flows along them, they generate magnetic fields. So we can surround the head with an array of very, very sensitive detectors, which looks a little bit like this, sort of helmet-shaped thing. You put your head into the helmet, detectors are around your head. And we can measure these magnetic fields. So in this case, these are the magnetic fields that are generated above the motor cortex. When somebody moves their fingers, the magnetic fields are generated by the currents that flow in our brains. We can then take those fields, we can apply a bunch of mathematical trickery, which I'm not going to go into, and we can end up with images that look a little bit like this, where the yellow blobs on the brain show which brain areas were active when a person was carrying out a particular task. So we can do this with very high spatial resolution, very high temporal resolution. And so MEG effectively is a very powerful way to measure what the neurons in our brains are doing. And as Stefano will say, I'm sure later, in a disorder like epilepsy, where the seizures that we see in epilepsy, for instance, are generated by abnormal electrical activity, then by measuring these magnetic fields and applying this source localization trick, we can actually work out where in the brain things were going wrong, where in the brain we have, let's say, aberrant electrical activity. So this is what a MEG system looks like. As I've already said, it's very powerful, but both from a research point of view to try and understand the brain, and from a clinical point of view to try to understand and manage different disorders. But there are a huge number of problems with it that all stem from one fact, and that is the magnetic fields from the brain, as you can imagine, are really small. They're absolutely tiny, sort of 1 billion times smaller than the magnetic fields that's all around us from the Earth. So to detect those magnetic fields, we need very sensitive detectors. And until very recently, the only real viable detector was called the superconducting quantum interference device, or SQUID. And to work, a SQUID needs to be cooled to liquid helium temperatures, so minus 269 degrees. So what you're actually seeing here is a cryogenic dewar. Inside there, an array of sensors, but those sensors are cooled to minus 269 degrees. That means that they have to be fixed in position. It means that they have to be a relatively long way away from the head, a few centimeters away from the head, because obviously we can't put something that's minus 269 degrees very close to the head. It means that this helmet is one size fits all. So, you know, it's great if your head happens to fit it, but if you happen to be a baby and your head is too small, then it's not great. And of course, if you move relative to this helmet during a scan, then that significantly degrades the quality of the data. So the vision really, from a quantum technology point of view, is to try and move away from this very large system, which incidentally costs about £2.5 million, and towards something like this, something which has got detectors that we can put very close to the scalp so we get increased sensitivity. Perhaps something that's wearable so it can move with the head. So if the patient moves during a scan, it doesn't matter. So that's really where we're trying to aim with this. And the technology that's really made this a reality is something called the optically pumped magnetometer. Now, I'm not going to go into huge amounts of detail because Carolyn's going to discuss this in detail in the next talk, but very, very briefly, this is what an OPM or an optically pumped magnetometer might look like. These are commercial OPMs built in the States. The essential idea is that you have some sort of light source, a laser, which is fired through a glass cell containing a vapor cell containing some atoms. So what we do by shining the light through the atoms, we actually polarize them. We polarize their magnetic moment through this technique called optical pumping, and that polarization effectively makes the vapor sort of magnetic. It has a magnetic polarization, and by examining how that polarization interacts with surrounding fields, we can actually measure what those surrounding fields are. Again, I don't want to go into any more detail because I think Carolyn's going to cover this later. What I will do is tell you a little bit about some of the things that we've been doing. So this has really been a sort of 5-year journey. And again, this is our sort of state-of-the-art cryogenic system. We started in 2016 with simulations and mathematical modeling to see how an OPM system might be used. By 2017, we had a single OPM system that we were using to try and measure the magnetic fields from the brain. In 2018, we had a major breakthrough because we were able to show for the first time that people could move whilst we were scanning them. So all of a sudden, you don't have to keep still in this giant helmet. You can move your head around freely whilst you're being scanned. And I won't go through all of these different developments, but where we are right now is this system, which is a 50-channel whole head system, which we believe, at least as far as we can tell right now, this 50-channel system performs at least as well as the conventional MEG system, but with the added advantage that you can move your head freely during a scan. So this is just to summarize what the system looks like. So we've got an array of our OPM sensors on the head. Person sits on a nice comfortable chair, pulls on the helmet. They sit at the center of a room. There is a magnetically shielded room around this system, and that's to serves two purposes actually. It reduces interference from things like laboratory equipment, mains electricity, things like that, all of which generate magnetic fields. So that is partly removed by the MSR, and it also dampens down the Earth's magnetic field, which is very, very important to actually make these sensors work. Surrounding the head, we have some fairly large planar coils, which also act to really accurately control the background field. And I do stress, without this accurate control of the background field, it's very, very hard to make even the OPMs work, let alone measure the very, very small magnetic fields that are generated by the brain. So, and then of course, over on the other side, outside the shielded room, we have all of the control systems. So PCs to control the OPMs, PCs to control stimuli that might be presented to the subject to evoke the brain activity that we actually want to measure. But that's the basic components of the system. So we have an OPM array, an array of 50 OPMs attached to the head, as in the image on the left. We have a magnetically shielded room, and we have a set of coils which work together. The MSR and the coils work together to control the magnetic environment. So in the last few minutes of my part of this, I just wanted to show you perhaps a few examples of the kind of things that we can do with this system. And I will leave it to both your imagination and Stefano later to talk through why these things might actually be useful. But this was a sort of fun example that we came up with very early on. So this is our system as it was in 2018. It had 13 sensors covering the right motor cortex, and we wanted to really show that you could indeed move your head and we could measure brain activity. So what we did, we got our subject here to play ping pong, and we tried to map the regions of her brain that were controlling that arm and elbow and wrist movement. And the results that we got were really quite striking. So despite completely unpredictable head movement, we were actually able to map. So this spatial image here, the little pink blob, shows the parts of the brain that control the arm and the wrist. And we got really nice data showing what was happening in an electrophysiological sense. So these are electrophysiological imaging data now, showing that at about a frequency of about 20 hertz, we get this large effect, this switch off of the 20 hertz oscillation caused by this, this paradigm. Now, so why is that of any use? Well, of course, there's a neuroscientific point here. Sort of interesting to work out how the brain does this very fine motor control. But perhaps from a more clinical point of view, if you can scan somebody while they're playing ping pong, perhaps you can scan an epilepsy patient while they're moving uncontrollably during a seizure. So that's the real point to, or equivalently, a Parkinson's disease patient who has tremor dominant Parkinson's, who finds it very hard to keep still. All of a sudden we can start to think about scanning them, or even infants. Kids find it very difficult to stay still in scanners. With infants in mind, in 2019, last year, we tried to do some of the first measurements in very young children. This is not a very young child. This is one of our colleagues, and we managed to get very nice somatosensory data from him. So this was a paradigm where people just gently touch the back of, the palm of somebody's hand. We got very nice beta band desynchronization, again with about, I think this was about 12 or 14 sensors. And then we tried the same thing in a 5-year-old, different helmet because they've got a smaller head, but same result. And then we tried the same thing in a 2-year-old, again, smaller head, but the same result. So we're really starting to see that we can now adapt a system to different head shapes, different head sizes, and still get pretty good data. Just throwing this in because it was sort of fun example. What we're talking about here is functional imaging. So we want to, in some way, evoke brain function. And there's a limited amount of function you can evoke by just letting people watch a screen. So it's great if you want to know what the brain does when you look at a picture or something like that. But what happens if you want to know what happens when an individual suffers from stress or anxiety or something like that? Very hard to make somebody stressed just by showing them a picture. It's possible, but it's hard. So we started to think about virtual reality, and we actually showed that you can put somebody in a virtual environment where clearly they can experience anything that you can almost imagine. So in this particular case, we had people leaning either left or right around a pillar that was in this virtual room. So they had to move their head either to the right or to the left. And when they leant around the pillar, they could see in the background this sort of chessboard pattern. And we were able to map brain activity very accurately that was evoked by the chessboard pattern. So when the chessboard pattern appeared on the right-hand side of their visual field, the activity in the brain appeared on the left and vice versa. We've compared this to probably the best available current technology in hospitals, which is electroencephalography or EEG. EEG is a mainstay of hospital clinical neurophysiology departments. What we found was that, first of all, EEG is around 10 times more sensitive to artifacts caused by head movement. So here's our OPM MEG and our EEG signal when the person was really still. These are recorded simultaneously. And here's what happens when the person starts to move. We get these horrible artifacts in EEG. The signal's barely visible, whereas our MEG really doesn't change that much from the initial situation. Of course, the physics of EEG and MEG mean that EEG has much, much poorer spatial resolution. So it's very, very difficult to get really accurate, pinpointed images showing which parts of the brain are active with EEG. Whereas MEG is much better, and OPM MEG adds even more. I'll finish with this slide because I know I'm nearly out of time. So, so this is something that was actually done in our lab over very, very recent weeks. So these are hot off the press results. Again, this speaks to the motion robustness of the system. So what this was really a neuroscience study, and what we were looking at here was the brain activity that's evoked when a person tries to play a musical instrument. It does need to be a non-magnetic musical instrument, and the only non-magnetic musical instrument we could get hold of was a very cheap ukulele. But nevertheless, we got our subjects playing this ukulele. We were able to map very nicely. You can just about see, sorry, this is a bit small, but you can just about see the little blue blobs on the brain, which is where the brain was firing. We measured these neurophysiological signals, and to cut to the chase, actually what we found is at least in 2 of our 3 subjects, we found significantly different brain activity when the person was correctly playing the chord sequence compared to when they were incorrectly playing the chord sequence. So actually we had higher beta band activity when the chords were played correctly compared to when they were played incorrectly. So I will more or less finish there and very quickly just say that I think there are really 4 advantages of this system over conventional MEG. So we can get closer to the brain, meaning higher sensitivity and better spatial precision. The flexibility of sensor placement allows this thing to adapt to any head shape, so we can scan babies and children as well as adults. Wearability means the system moves with the head, and by accurately controlling background field, and again, I stress that's really important, but assuming we can control background fields adequately, we can have people moving during a scan, so you no longer have to keep still in a scanner. Whoops. And finally, even at this early stage, this system is around half the price of a conventional MEG system. And I think Carolyn might talk a little bit more about how we can make this system more scalable and therefore fit it within the budget of a hospital neurophysiology department. Lots of different clinical applications that I'm not going to go into, but yes, COVID-19 is one of them. I think perhaps the most obvious though is epilepsy, and I know Stefano is going to talk about that. With that, I'll thank all of our colleagues past and present, and in particular the guys at QSpin who make all of this possible with their sensors, the guys at UCL, Aston, Sick Kids, Oxford, and thank you all for listening. Happy to take any questions now or during the discussion later.
This is Bob. I've been monitoring the Q&A. We've got a number of questions coming in. Maybe some of them will have to wait until the panel session later. And the first one, we had a question on what is the spatial resolution of MEG, and later on a question, what is the temporal resolution?
I'll start with the easy one first. The temporal resolution depends on the temporal resolution of the sensors. So at the moment, the frequency that we can get up to is about 130, 140 hertz. So that's, you know, the temporal resolution is a few milliseconds. We may talk later, there are ways to change that. That's with an OPM system. With a squid system, it's slightly higher. Spatial resolution is a really tricky question to answer, actually, because it's not as simple as you might hope. It does depend not only on how many sensors you've got and where you put those sensors, but also the proximity of those sensors to the head and the signal to noise ratio of the data. What we do know is as you move further away from the head, the magnetic fields that you measure get more diffuse spatially. So as you come closer, you get higher spatial frequencies. So that means that as we move from a squid-based system where the sensors need to be a long way away to an OPM-based system where the sensors can be right on the scalp surface, you vastly improve the spatial resolution. To try and put some numbers to all of that, because I sort of realize I'm waffling, in a conventional MEG system, maybe 5 to 8 millimeters, something like that. In an OPM system, in theory, 1 or 2 millimeters. But in practice, it's never yet been proved. Remember, these are early days.
Thanks. A question, how deep in the brain can you go with this technique? That's a
great question. And probably most people might know that the field from the brain falls as the inverse square of distance. So if you double the distance to a particular structure, you will quarter the amount of signal that you get. So going deep is a challenge. Nevertheless, it is possible. We're working with our colleagues at UCL. Gareth Barnes and his group have recently published data showing that you can get all the way down to the hippocampus, which is a relatively deep brain structure. So it is possible. You need a combination of clever experimental design to get a big signal, and also clever array design. Just to add to that, I think one of the most remarkable things that I've seen with an OPM is that actually the signal from the hippocampus is very, very deep. And in terms of accessible areas, the signal from the hippocampus is actually quite large in the roof of the mouth. So one of the things that the UCL group did was actually put a sensor in the roof of the mouth and show that you could measure hippocampal magnetic fields from inside the mouth, which was, I think, remarkable, really.
Just jumping to another question, does OPM MEG allow you to measure gamma band activity consistently as conventional MEG or EEG?
Yes, it does. So we have routinely measured gamma band activity with OPM MEG. Bizarrely, it's actually quite easy because it's the noise spectrum of the OPMs that we use is incredibly flat. It's really quite nice in the gamma band. So anything up to 120, 130 hertz, absolutely fine. So we routinely measure visual gamma. Yeah, it's probably worth saying, I think we're better at measuring visual gamma with OPMs than we are with conventional MEG, but we're certainly much better than we are with EEG, because EEG has a big confound in the gamma band, and that is muscle artifacts. I sort of alluded to it very quickly in the talk, but so when you tense the muscles in your head or you move your head, you get these muscle artifacts. It's electrical activity from muscle that you don't care about because you're trying to measure the brain, but it affects the sensors. And it affects the gamma band in particular, and so that artifact exists in MEG, but it's about 10 times lower.
Thanks. Just 2 questions which I'll combine into one. What is the setup time, and how accurately do you have to position the sensors?
Again, the 2 very, very good questions. Setup time, 2 or 3 minutes. Depends on who you're scanning. So, you know, if I happen to be scanning one of my colleagues, it's probably more like 30 seconds. If I want to go through the niceties of if we were scanning somebody who perhaps never been in before, you want to explain to them what's going to happen, you want to explain what all these kit does, then you would take more time. But to actually put the system on is very, very quick. There's a little bit of setup in terms of switching the sensors on, but that can be all done before the participant actually arrives. Sorry, remind me the second part of that question.
There was, how accurately do you have to position the sensors?
Sorry, yes. So we do need to know, in order to get the really pretty images of brain activity, we do need to know where the sensors are relative to brain structure, and that is a challenge. So at the moment we use an optical camera, which is a 3D camera, and you can take a 3D image of the face and the sensors, and from that you can actually work it out, and we get it to within around about 5 millimeters, I think, which is probably comparable with where we know head position in a conventional MEG scanner.
Thanks. We do have a lot more questions. I'll save them for the panel session later because we're over time already, to hand over to Caroline.
So good morning. My name is Carolyn. I'm an experimental physicist working in the Experimental Quantum Optics and Photonics group in the University of Strathclyde. And this morning I will speak about the sensor side of things. Matt has done a fantastic job in really setting me up for the big why of why do we want to do brain imaging. And I'll speak in more detail about the type of sensor that we're going to use to do that. So, or is already in use doing that. So I'll talk about zero field, optically pumped magnetometers, and I'll explain what all of those terms mean as we go along. So our group is funded and we're part of the UK Quantum Technology Hub, specifically in our group for sensing and metrology, although there's a few other components to that. We really like building sensors and instruments that are used for application, really applications-driven approach. So we build atomic clocks for doing things like improving timing for GPS. We make rotation measurements for GPS-denied navigation on aircraft and things like that. And then we do magnetometry for a whole variety of interesting applications, including things like cardiography, magnetocardiography for cows. So that's where we come from. How do we make a measurement? Well, in the most simplistic sense, taking a measurement involves identifying a signal of interest that we want to measure, and that needs to be some changing property. And then we build a device that responds in a predictable way to the changing property. And then, of course, we need to record the data that it takes and process it, and then present it in such a way that it can be read and understood. And so the device that you build must be sensitive enough to detect the signal of interest. And really this comes down to scale. So Matt touched on this a bit already. There's a whole lot of interesting magnetic noise in our day-to-day lives, and really the main one is this static magnetic field that's due to the Earth's geodynamo. And that's at about 50 microtesla at this latitude where I am in Glasgow. And I've put up a few other kind of household magnetic items, whether that's static magnetism, so some actual ferromagnetic object, or current flowing, creating a magnetic field in the form of electricity, or light bulbs in your room. And then, of course, on the lower end of the spectrum, we have clinical applications. So your heart and your brain both have electrical currents that generate magnetic fields. And we've already, in our group, built sensors that operate on this kind of scale. So we're able to measure this kind of magnitude of field. But for brain imaging applications, we can expect anywhere between 1 and 100 femtotesla magnetic signal. And it's pretty tricky to detect fields this small in the background of something like the Earth's field. So at this stage, we've made sensors for these kind of applications, but we really need to move to a different measurement scheme if we're interested in making measurements of the brain. And that measurement scheme is zero field magnetometry. And that's really where the shielded rooms come in that Matt mentioned, and these kind of compensation methods. And this gives you a better overview of the kinds of applications that fall into unshielded versus shielded sensors. This unshielded sensors that we've built already fall into some interesting categories, as I mentioned, bovine cardiography, things like nuclear threat detection, surveying for geology and things like that. And it's important to make this distinction here because creating a shielded environment is far from trivial. So we have all these fantastic magnetically shielded rooms in hospitals and research centers. And this really means that we have a nice quiet environment where it's free from large amplitude magnetic noise so that we can take these very sensitive measurements of the brain and the heart. And the technologies that we already have for doing magnetic sensing, most of you will probably already have a magnetic sensor or 3 in your phone. These Hall effect sensors are really ubiquitous in most smartphones. So any phone that can do navigation will likely have one of these. But they're not particularly sensitive, is the one drawback. Things like flux gates are really widely used in surveying, have been for many years. They're significantly more portable than some, but they are still unwieldy. And there is a bit of a drawback in terms of sensitivity with respect to brain imaging. And then really the state of the art in MEG for many years has been the squid sensor. And the drawbacks, as Matt outlined earlier, are really that you have a fixed dewar shape. So you're really limited in terms of if you have a different sized head or a different shaped head, how close you can get the sensors inside of this dewar of liquid helium to your head. And that really plays a role in when you're doing interesting things like they are in Nottingham to do source localization. So this inflexibility of position is a really big problem with squids. And in the last 10 years or so, optically pumped magnetometers have made huge progress in terms of both sensitivity and in size. So I believe at this stage OPMs can now actually outpace squids when it comes to sensitivity. So this is actually a commercial product. This is the QSpin Gen 2 zero field magnetometer. This is really the state of the art at the moment. This is the state of the art in OPMs for MEG. However, it comes with a pretty large price tag. I believe that the cost for buying one sensor is about £10,000. It's made in the US, so it potentially comes under ITAR restrictions. So we would really like to build an OPM of our own, improve the UK supply chain of OPMs, and have a kind of a flexibility in the design, so we can decide whether how to trade off on sensitivity and size. So these are the specifications that we really want to work towards when we build an OPM specifically for MEG. It must be sensitive, so we need low systematic noise, and we need to be able to hit these numbers of 1 to 100 femtotesla. It needs to be compact, so we need to be able to fit a lot of them on a patient's head, and it must have a low standoff distance, so where the actual sensor volume must be as close to the scalp as possible. We need to be able to scale it to arrays, so we need to be able to have many sensors synchronized, and that they must not have crosstalk between them so that they don't interfere with one another. And in applications such as MEG, where the sensor must be close to the skin, the low operating temperature is really, really important, because you just cannot put a hot sensor next to someone's head, never mind 30 of them. And then, of course, we'd like to hit low cost. So we would like to make these for significantly less money than you can buy the current commercially available sensors. And in our group, we're in the business of using lasers to manipulate atoms in order to take measurements. And atoms are a really nice system to work with. Specifically, the alkali atoms are, if you remember from high school chemistry, they're under hydrogen on the periodic table, and they almost act like hydrogen in many ways. So they have a single electron in the outer shell. They're predictable, and the theory and experiment agree really well for these systems. So many of the lasers that have been developed for the telecoms industry, the wavelengths and frequency range that they have corresponds actually really well with those needed to excite alkali atoms. And so that's really convenient for us. So that's really the atomic part of the name in atomic magnetometry. Where the optically pumped aspect comes in, as Matt briefly mentioned earlier, the way we're going to interact with these atoms and how we're going to take our measurement is really important. So we have some atoms in a gas or in a vapor contained in some environment, and they're randomly oriented. So their spins are randomly oriented to begin with. We take laser light and we optically pump the atoms into this magnetized state where they're aligned along the beam. And then if we have some magnetic field, say some signal from the brain, in the proximity of the atoms have this really nice property where they actually precess around the field. And the frequency that they precess at is proportional to the field. So we have this proportional response to our signal, which is the signal is the Larmor frequency. And we have this gyromagnetic ratio, which is just a constant of proportionality. And as long as we can accurately measure that frequency response, then we are certain of the signal. And really detecting a frequency is one of the nicest ways to make a measurement because you're essentially counting. And in addition, using atoms, this is a calibration-free measurement. So the response that we measure directly produces the signal of interest every time. And where the zero field comes into the name here, we're essentially placing this sensor, placing these atoms in a very low field environment. And we have this response around zero. So at zero magnetic field, we have this shape. And I told you that the frequency of precession is directly proportional to the magnetic field. So as the field changes, if we have some signal from the brain, for example, then the response moves proportionally away from zero. And if we can track that change when we read out the frequency, we can track the field. And that is fundamentally the physics behind these sensors. So in practice, what this device might look like, this is a schematic of the kinds of components that we need to include. What we have really at the heart of it is a gas of atoms enclosed in an atomic vapor cell. And we need to heat this cell in order to get sufficient atoms in the vapor. So otherwise they'll stick to the walls. So we heat these up, we get enough atoms to get a good signal. And then we use a laser beam to pump the atoms as I described. And then we use the same laser beam to imprint the frequency of precession is imprinted on the laser beam. And when we detect this beam using a detector, that is how we read out the frequency. So it's actually quite a simple setup as far as atomic physics experiments can go. There are relatively few components, but the components that we choose are extremely important to really get to the sensitivity that we require and also the size. There's a lot of engineering involved here. And we've previously managed to build a magnetometer with these components into a 20mm package. And the components are fundamentally the same. There's just a few differences to the way that we operate the sensor. So first up is the laser. Up to now, we've been using these vertical cavity surface emitting lasers. They are a commercial product. I found out yesterday that they're actually used in computer mice already and things like facial recognition technology. So these are these are a semiconductor laser that are fabricated on a big wafer and then spliced and put into smaller packages. And so inherently that is very scalable. And what we really need from these devices is that they're tunable so that we can select the wavelength that we want, wavelength of light, and that they're stable so that when we ask for a certain wavelength, we get that wavelength for as long a period of time as possible so that the sensor is stable. And really the heart of the sensor is the atomic vapor cell. So we spend a lot of time thinking about this, how to make these better. And fundamentally, it's a container for the atoms. We need it so that there's optical access, so the laser beam can get through it. And in the case of these, we also include buffer gas. So here we include nitrogen as well as our alkali atom in order to control the motion of the atoms. So we need to be able to heat it to above 100 degrees C. So primarily these are silicone or glass based. They are all created on either a silicon wafer or a sheet of glass and produced in large batches. So in the case of the silicone, we have a large silicon wafer that is etched, chemically etched, and then sandwiched between two layers of glass. And in the case of these glass cells, we've actually water jetted these to get the optical access and the space for the atoms. And we've been producing our own cells for a little while now. And what's really nice about that is we get to tune different parameters such as, length and window size and buffer gas pressure. So that's been really important in improving our devices. And then we've also really gone down the route of making custom electronics for low noise heating and detection. So essentially, if you want to heat up this atomic vapor cell, at the moment we're using resistive heating, and if you pass a current through a resistor or any wire, you're going to produce a magnetic field. And we really do not want to create any additional fields in the region of the cell. So we've had to be quite clever in how we've designed our heating system. And we believe we've managed to figure out a way to do it without introducing significant noise to the system. And as far as detection goes, we use 2 photodiodes for detection. And again, we've gone down the route of building our own PCBs to do so. The current scheme that we're using, the detector is between the cell and the patient's scalp. So it really needs to be as compact as possible to minimize the distance between the sensor volume and the head. And really having the expertise to design these kind of components is a huge advantage. And the fact that they're built on PCBs really speaks to the fact that they are scalable. You have to order about 10 at a time when we build them. And so far on this project, as to where the state of play is at the moment, we are very much still in the lab. What we tend to start with is a lab-based experiment that looks, well, you can't see inside here, but the experiment is all housed in this mu metal shield. Hopefully the schematic gives you an idea of what that looks like inside. But basically we start with a lab-based experiment in a very well-controlled environment. So in order that we understand the physics of what's going on and we can optimize certain things as we go. And we use this setup to test many of these portable components that I mentioned, so that we're testing them in a well-controlled environment, so that when we move to a portable package, we really nail down everything we need. And we've tried to build it in as scalable a way as possible, so that this is straightforward to scale. And we already have a track record of taking experiments out of the lab. So this device here is one of our unshielded sensor heads. So this is just a different type of magnetometer. It doesn't have the sensitivity required for MEG, and that's why we won't use it. But the electronics and the control systems are separate, and really this gives us an idea of where we want to go with building sensor heads for MEG. It is truly portable. This photograph was taken in my colleague's garden, and we've taken them to field trials and public events. It can measure things like a drone taking off nearby, or my colleague recently measured the magnetic field due to his bird feeder swinging next to the device in his garden. And as part of this unshielded sensor, we have already developed control systems to read and operate multiple sensor heads. So my colleague has built a system around an FPGA, which does everything from the timing of these devices to the data processing. It controls the heater and the laser, and is basically fully integrated. And this type of system is really well placed to control an array of zero field sensors. So at the moment, this can control up to 8, and we're hoping to scale that up to 16 soon. So some of the key challenges that we need to address in the next little while are, first of all, heating. So I told you we need to heat this atomic vapor cell. It needs to be, by our best estimates, about 110 degrees C. And of course, we can't put a sensor that is 110 degrees C next to a patient's scalp. So we really need to address this, how we're going to either insulate or do something else clever to make sure that the sensor, where the sensor touches the patient is not hot, especially if you're going to have an array of these on your head. That really matters. We're looking at our laser supply chain in order to really nail down these packages with the exact parameters that we're interested in. And we've already been testing vapor cells in the lab so that we can really improve our cell design to suit the application that we're interested in. So doing things like looking at different geometries and fill pressures will be important. Next, kind of on the agenda is exploring different sensor geometries or different sensor configurations. So we'd like to stick 2 cells inside the sensor, and that really gives us an advantage in terms of it can be used to cancel common mode noise. And then it also gives us additional information about the field from the brain because it can give us information on field gradients. So where we are at the moment, we have completed our lab-based experiment just after our first lockdown in Scotland. The data on the right is the zero field resonance that we've managed to acquire. And what this does is allows us to measure changing magnetic fields. The really nice thing is that the experiment now runs remotely, so we won't be caught out by another 6 months out of the lab. So I actually took this data from my desk at home last night. And really what's next in the lab is to do some optimization, and so really improve the signal to noise and improve the sensitivity of the device. And on that end, we really want to compare the sensitivity of the device we build to the ones that are already on the market, and really make sure that we hit the benchmarks we've set for ourselves. And then we'll continue to do portable component testing in the lab environment. So there's a lot of optimization to do, but things are looking good since we got this signal recently. And finally, I'd just like to thank all my colleagues for their work on this project, and thank you all very much for your attention. So I'll be happy to take any questions.
A few questions have come in on the chat, actually more than we can deal with now. But if we just take a couple of quick ones, how many OPM sensors do you need for an OPM MEG helmet?
Let me just see. So I think that's probably more Matt's wheelhouse. I myself have never actually done any MEG, but we're happy to make as many sensors as he asks for.
I can speak very quickly to that. I think the answer is you can never have too many, and we know, so it's a law of diminishing returns. So you need probably at least 40 or 50 to get reasonable spatial resolution and whole head coverage. We know that actually things carry on improving up to around well over 1,000 sensors. So that's what the mathematics tells us. So it's a case of having a pragmatic approach. But with 50 sensors, we think we can get about equivalent performance to a cryogenic system. But Carolyn, if you could give us 1,000, that would be great.
I'm not sure I can give you 1,000 small enough to fit on the head. We are fundamentally limited in some areas.
Mm-hmm. Just one more question. What line width does your laser source need to be, and how well polarized does it need to be?
The line width doesn't, so because we have quite optically broad absorption peaks in our, we've introduced buffer gas to our atomic cells, and so actually the absorption peak is quite wide, and so we have quite a high tolerance for the line width of the laser. So in the lab we use a pretty narrow laser, order of tens of kilohertz, I think. But in practice, we found that it doesn't make a huge difference, and we can certainly live with the line widths that VCSELs provide us. Was there a second part to that question?
Polarization.
Polarization. So the VCSELs are, well, that's something we need to explore. Certainly, there does seem to be a large polarization dependence on signal to noise in things like double resonance magnetometers, so the unshielded ones I spoke about earlier. In the surf sensor, that is one parameter we have yet to explore, but we do expect it to have an important to be important. Luckily, the VCSEL polarization seems to be pretty stable, so they come out. The light comes out of the VCSEL fairly well linearly polarized, and so it should just be a matter of a couple of optics to sort that out.
Thanks. We do have more questions, but we do need to move on to Stefano now. We'll come back to the unanswered questions.
Here I am. Thank you. Thanks, Bob, and thank you everybody for having me here. I think the level, at least the scientific level of the webinar, is going to have a significant drop at this point because you've invited a doctor, so things are not going to look that good. But anyway, I'm going to try and do my best. You'll hear a lot of, in my experience, which is a typical medical way of approaching things. So apologies for that. But the other point I'm going to try and make is that I have no disclosures to make. They haven't paid for the ticket to the Caribbeans that you can see in my picture. I'm actually broadcasting from home anyway, so it's just I was asked to review a little bit about how MEG has evolved in the clinical world and what kind of footprint it's made. And I think it's two stories essentially. One is the incredible growth that scientific contributions have experienced in the last decade. Certainly, I've just taken out, the last 8 months or 9 months of 2020 just to look at what's been happening, and you can see, there's studies that have covered pretty much all the areas that Matt has indicated in his initial presentation. So epilepsy being the largest, because ultimately most of these techniques ask a question as to where before the interesting part of how and what do we learn from it. And schizophrenia, psychiatric disorders in general have a large chunk. Autism, neurodegenerative conditions is certainly the disease of the century and the future. So there will be dementia and other will cover pretty much probably the next decade or so. And we've seen finally people leaving out their kind of personal approach to medicine and to try and come out at least with a set of clinical guidelines, as we have for any other technology that we use in diagnosis of neurological disorders. On the other hand, you can look at phrases extrapolated from presentations of people that have worked in the field. The acknowledgement that there's still quite disparity in spite of these guidelines, and that this is actually a study that we conducted in Europe to look at where clinical MEG is, where harmonization is still not there in terms of how we use the technology. In the last International Clinical Neurophysiology meeting in 2018, the question of where is MEG going was raised. And I think there's all of these indications will tell you that there's a lot going on, but before we can really say that we have a unified approach and we can share data, I think we're still not there. This is the study that we conducted in Europe, collecting information from other centers around Europe, and we only received data from centers that are actively involved in clinical activity, and you can see that in most cases, preoperative mapping of what we call eloquent cortex, so parts of the brain that perform key functions like movement, like language or memory, etc., was the main application. So what are the operational challenges? I would say that the first and foremost, it'll be money. It'll be down to money. And the squid-based systems, as it's been highlighted and Matt has made it quite clear, are very, very expensive. So when you look at the depreciation of the system and the need to have a throughput that justifies that that depreciation is really looking at about between 10 and 15,000 pounds per test is what the hospitals, I'm talking about Cleveland Clinic, which is the largest provider in the US, for example, are aiming to receive from insurance companies. Actually, that is significantly less, because in the States there's a very articulate process about how that money is reimbursed. That's partly responsible for the relatively low penetrance. In the UK, there are quite a lot of labs that are able to perform. There were about 12, I think they're growing, laboratories. There was an initiative that we've all been involved in with the MRC funding to look at clinical application and way to the clinical application, but it's still relatively low. As far as I know, Aston University, where I work, is still the only real center that has a large throughput of patient in the UK. We get referrals from everywhere around the UK, but there are still centers that do the occasional patient at the moment. Things are going to change clearly, and that's good. That's good for the community. The other challenge is obviously, as I've mentioned, the difficulty in standardizing procedures. And obviously, when you look at performing meta-analysis, trying to answer big questions with small data which are dishomogeneous, and that becomes a major problem. And user interface of the systems, I think that technology is always exciting and wonderful, you know, gyromagnetic ratios and this and the other. But ultimately, what you need is something that a simple doctor or a clinical scientist, what we used to call technician, is able to operate. And MRI should teach us a lesson where, you know, you can run an fMRI motor paradigm in 20 minutes, and most radiographers know how to do that. But for MEG, we're not quite there yet. And the other problem is obviously that to do what we do, which is to go from the signal space that again, I'm referring to the presentation that Matt has given, to source space. So where is it coming from? We're mostly using open source software. There's no clinical validation. There's issues about, obviously, the ability of any clinician to take responsibility directly for what is being done. There's also specific challenges in pediatric age. I mean, on the left is our old system, which isn't really old, but it's just the system we had before. It's currently sitting in Venice in Italy, and it's a 275 channel MEG system, and the 306 channel system on the right is the current one. And you can see what a kid has to go through in terms of pillows or booster seats to actually get anywhere near the top of the door. And these are even smaller children. These are children that we've conducted a study on who have liver transplant. That's why they have all those devices attached and nasogastric tubes. And so it's extremely difficult. And I think the pictures that both Matt and Susan have shown are really, really encouraging. This is just to show you when we look at the design of a helmet and the difference in terms of how high can you go, and obviously there's the issue of shoulders as well that are preventing people from getting too close to the top. You know, for smaller kids, it's extremely difficult. And this is particularly important for children with developmental disabilities or developmental disorders, and epilepsy in particular. So if you look at the green lines here, you can see that this is the head size of a group of kids with epilepsy and other problems that will end up at our center to be assessed for potential surgical treatment of their epilepsy. And you can see that they sit very low with respect to the average of their peers, which makes it even more difficult. Yeah, you can stop kids from moving, but I don't think this is allowed under current regulations. So we have to think of more clever ways of doing that. And the impact of movement and distance are quite significant. Matt has clearly explained that moving away 1 centimeter or 2 centimeters is not linear, and the SNR changes so drastically as you move away from the sensor that this is a problem that we haven't resolved, but we need to. I'm just going to show you a little bit about epilepsy, which is the most frequently used application, but that's not the only one, of course. And you can see that it pretty much matches what we do for a standard test in an EEG department, where you measured your electrical currents on the scalp using little cup electrodes that are attached to your scalp. You go through the referral screening form with the added caveat that we have to adopt almost MRI level kind of screening forms, not because we have worried about the person, but we were worried about the equipment. Obviously, ferromagnetic material in an MEG room is not ideal. In fact, it's pretty bad. And the rest is pretty much what we do. The only other issue is that those beautiful pictures that you've seen up to now will require having available an MRI of the individual person, or as we have done, our laboratory has done, looking at how to use normative MRIs to best fit the head of the person. So going from the live measurements on the individual, picking the best fitting MRI to do the job. In most cases, in hospital level, when you're assessed for epilepsy surgery, obviously you will have had an MRI as part of your treatment. And then, I sit with my colleague scientists who are extremely clever in doing analysis and interpret the data. What we do is we look at stuff that's usually should be there. We look at what we call interictal epileptiform discharges. They're transient. They're very short-lasting elements that appear in the ongoing EEG. We have to divide them by their topography and look at maybe averaging them out and looking at improving signal to noise ratio and localizing them. There are many ways of doing that, and this is one where we've worked quite hard to apply clinically. You end up effectively with a number of traces like the one that I'm showing with hopefully you can see the mouse hovering, which is actually the activity at one particular voxel in the brain. And that activity is pretty much looks like, and take my word for it, what you see when you actually implant electrodes in the depth of the brain of the individual. And you can see the normal rhythmic activity, and then you can see these transients that appear. And these are usually hallmark of a brain that is prone to have seizures. We can place them in three-dimensional space in the MRI of the individual. This is a kid that was referred to us because he was having constant motor seizures affecting the lower limb. And you can see that it pretty much matches where you'd expect the motor representation of the lower limb to be. So very much, very accurate. Other examples that I can show you are patients with large lesions of the brain, where we try to resect as small as possible an area of the brain to prevent the person from having deficits at the end. And the problem is obviously that you can have 1,000 obviously lines, 1,000 sensors, but ultimately if you're asking me to interpret a page of 1,000 sensors, it becomes quite difficult. Looking at the reciprocal relationship between various points in the scalp is extremely difficult. So we can't really interpret 1,000 lines. We need some way to put it in the MR of the brain of the person. So these are the transients as they appear, what we call interictal epileptiform discharges. And this is their location. I mean, you'll have to take my word for it if you're not a neurologist or a neuroradiologist, but this is the healthy part of the brain on the left side of the middle picture in the top. And the other area where you see the orange activation pattern is totally different in shape and form, and that is what we call a focal cortical dysplasia, an area of abnormal tissue formation. Look at the next on the right. So this would be the healthy side on the left, and this would be the abnormal tissue on the right. And we can, yes, we can localize quite in depth. We can have some discussion about that, but certainly we have localized as deep as the insula and the hippocampus and verified with intracranial recording. So I can vouch for the resolution in depth of the current systems, and certainly that's something. The way we use MEG at the moment, this is an old paper that we published some years ago, but I think it's informed our practice in the future. We did it in collaboration with our colleagues at King's College in London, and is to actually guide the implantation of electrodes. So if you look at the page, the slide on the left side of this slide is the actual traces, and the images are showing you the activation, the area where the abnormal activity is on the brain of this particular abnormality, and we can map this activity also onto the array of recording electrodes that my colleagues at King's at the time had placed on the individual patient. And actually we could capture a seizure originated on that area. That area had been declared as normal by the radiologist initially. Looking back, we have histology that has shown that actually it was an abnormal cortex, it was a focal cortical dysplasia. So MAG is able to inform more invasive recordings at the moment. We may be able even to do without them in the future. Seizures are very difficult to record. This is one of the few that we captured. Unfortunately, our system is not in a hospital environment. It's in a clinical research facility. So patients who are acutely ill cannot be admitted. But we have captured a few seizures. This is what we call a temporal lobe seizure of a patient, where there's usually a change in sensation and feeling about the environment. There's no major motor manifestation. And we can track in time the activation pattern. This is the area that's abnormal anatomically, and the area surrounding it is usually the one that produces the seizures, and that's the case for this patient. So the patient was operated with a larger resection and became seizure-free. So we've had so far, I mean, that was done at the beginning of the year. We haven't had much referrals, as you can imagine, due to the pandemic, but we've done about 500 patient studies, and a small percentage don't have any abnormalities on the scalp. And that's an issue that needs to be resolved. What do we do with this data? Some of them have abnormality, but not of the type that I've shown you. And in general, it's been quite impactful in terms of what to do with the data. We brought it back to the colleagues, and we've identified at least one area which is potentially a candidate for resection in about 3/4 of the patient, which I think is extremely good. The other thing we can do is map function, like language, for example, where what are the critical areas of language? This is something we did a long time ago in healthy individuals, and we can actually do that also on patients. We've just published a paper a few months ago where we've reviewed all our activity in terms of language mapping and intraoperative verification, which is extremely encouraging. So we can actually preserve function by showing what areas of the brain, not only what hemisphere, but what areas of the brain are critical for language production. So my final considerations are that recording EEG at such high sampling rate and such high spatial sampling, it requires large data sets. And so if we divide data sets in chunks, we don't have continuity, we risk of losing some data. The analysis can be quite slow. So there's an issue about processing time and pipelines, which need improving. The MEG that I've shown you, so the MEG that uses squids, is sensitive to excessive movements. There's no doubt. There are ways to minimize that, but the current situation is as I've described, and it allows very limited use in recording of seizures themselves. It's not feasible at patients' bedside, which is a major problem. We admit patients for a week to capture some of their typical seizures, and we can't really do that with our current MEG system, of course. The sensitivity to the distance I've talked about, the helmet design, etc. There's an issue that's historically known from MEG about sensitivity to radial sources. I won't go into detail of that, but if not to say that in clinical practice this is virtually immaterial, because there's no patient with epilepsy, for example, who has a lesion that is right only on the convexity, and it doesn't involve at least some part of the enfolding of the brain. The other issue to think about is there's increasing research now looking at high frequency activity as biomarker of epileptic zone. So where is the technology going? Are we going to be able in the future to look at frequencies above 250 Hertz, which are of interest at the moment? And I think the last is implications. So we need to imagine that this technology will end up in departments where we have clinical scientists. We don't have a large number of physicists who can help us. And so we need pipelines, and we need to train the next generation. We need our community of clinicians to take stake and interact with the scientists and develop pipelines that will make this technology usable, not only in research laboratories, which offer their services to clinicians, but in clinical settings. And obviously, the other thing is we think of MEG only as in the source space, so only after we've calculated the inverse solution, but actually we can get important data from the scalp only. And I think that's an area that's been neglected quite a lot by our community. And I think I'll leave it here for discussion, and happy to take questions if anyone has any. Thank you.
Thanks very much, Stefano. We do have a number of questions, I think, for all the panelists that have come up. Perhaps I could just ask one. When do you see this becoming available routinely in hospitals? I remember when there were fundraising drives for CT scanners. Now it seems every hospital has got one. Where do you see this going in the future?
I think it's. I think the economic limitation posed by the 2.5 million that currently, and the space requirements. Don't forget that at least in the UK, there aren't that many new purpose-built hospitals developed. Most of them are refurbishments or adaptation. And actually, an MEG system like the one we use requires to be, as far as possible, for your MRI scanner, because they don't really like to be interacting with each other. They need a very, very powerful shielded room. They occupy quite a bit of space, and so between building costs and the system, you're looking at something that is not available, at least in certainly in the budget of my hospital. We've had fundraising activity with success to raise something in the region of £200,000 to £300,000. That's something that is within the realm of possibility in the current climate. But I think something like this requires obviously a bulk of data that show that it's a life-changing kind of technology, which we have, with the caveat of limitation I've shown, but also I think the logistics has to change. I don't think there are some hospitals in the States that have them in separate buildings. There's certainly Toronto has 2 systems. The children's sick kids, they have one in the hospital, an old CTF system. But not many hospitals, well, no hospital in the UK has one resident on site. And I think that is something that hopefully, I'm very excited about the presentation of Carolyn and Matt before. This is going to change in the future.
Thanks. We had a question early on. Do you use AI or machine learning for information extraction from the data? I guess that might apply to all of you.
I can perhaps speak to that first. Yes, we do. It's used in multiple different ways. We're actually using AI to advance neuroscience. So we're looking for features in the data that that tell us about networks and how different brain networks form and dissolve in order to support cognition. But we are also now using machine learning to try to identify features of epilepsy. So in particular, we're trying to use something called the hidden Markov model. This is work by one of my colleagues, Zaleka Sidat. We're trying to use a hidden Markov model to find epileptic spikes. So yes, we are doing that. It is obviously a huge area, and there are lots and lots of groups around the world who are trying to do it as well.
Thanks. Perhaps another question for Stefano. How valuable is the clinical information from MED? Is it significantly higher quality than EEG, for example?
That's a live debate. I think it's kept busy a lot of people and has pumped the publication record of many my colleagues. I think it really I think it's difficult to say something without saying that it is the devil is in the detail. So if we're looking at the accuracy in terms of our ability to detect abnormalities when they exist, we have to compare like for like, and certainly the spatial sampling of the routine EEG that we do in hospital with 21 or 19 sensors applied on the scalp cannot by its nature be compared to the density of the matrix of acquiring sensors that we use in MEG. However, it's undeniable, and Matt can give you all the details about the physics of it, that the fact that the EEG is so sensitive to zero phase lag to volume conduction effects is something that we can't just get around very easily. There are mathematical tools that enable you to make assumptions on the conductivity of the medium where we record, i.e. the interface between the scalp, skull, brain, CSF, etc. But MEG is inherently easier to deal with, and therefore I think if you're telling me, 100,000 for any 128 channel EEG versus 2.5 million, and you're asking me to do some calculation on value for money, I don't know. I mean, it'd be something to do, but I suspect that's not the point that my colleague is making, with this question. I think MEG has inherent advantages, and Matt, maybe you want to comment on this.
Yeah, I mean, I think MEG has two inherent advantages, as you say. The first is that you can get much better spatial data. So if you're trying to map the location of an epileptic network, then you can get much more accurate results with MEG than you can with EEG. And then the second thing I think is that EEG is much more sensitive to artifacts, as you say, Stefano, based on volume conduction, but also from muscles and things like that. I guess the point I would make is all of the data that Stefano has shown, brilliant as it is from conventional MEG. And as well as the increased practicality of OPMs, we also know that it's more sensitive because it gets closer to the scalp. And by getting close to the scalp, we pick up these higher spatial frequencies. So actually, OPM MEG is fundamentally more accurate than EEG. And I guess, Stefano, I'm going to be completely unfair to you and push back a question here, but I completely understand. So if you've got 100,000 or a couple of 100,000 for an EEG versus a 2.5 million MEG scanner, that's a difficult call to make, particularly when you're in a hospital where an MRI scanner will cost you 1 million, for instance. So this is 2.5 MRI scanners. So my unfair question to you would be, what price does an MEG system need to be before you would say okay, we're not going to buy an EEG anymore, we're going to buy an MEG? What number do we need to aim for?
Okay, so that I would say to you that okay, first of all, the MRI costs what it costs because of economy of scale, first and foremost.
Yeah.
So it's obviously inherently related to the fact that you know, the production cost of our MEG systems that we currently use, and I'd be delighted to present some data with OPMs when we work together at some point in the future. But I think I would say that anything around $250,000, between 200,000 and 300,000, is something that is reasonable to expect a system with those properties to be starting with. And but I'm pretty convinced that with technology evolving and economy of scale and becoming possible, those numbers are just numbers that you throw at the moment, but the curve of this price will probably follow the same curve as the MRI systems in the past. You know, we needed 2 million, probably 2.5, to have an MRI a few years ago. I've gone through commissioning 3 MRIs in our unit, and prices have gone down. So MEG prices haven't gone down, and I think it is because they're very few, and there's just no way that even the production costs are, you know, you can scale them effectively. So I would say, I think 300,000 is a good starting point. I don't know whether it sounds reasonable to those that are now embarking in this adventure, but that would be my estimate.
So I think at the moment the cost, so bearing in mind that this is very early days, at the moment the cost of an OPM MEG system is about 1.25 million. So it's about half the cost of a cryogenic system, and perhaps Carolyn could jump in here. So the vast majority of that cost of the 1.25 million is the sensors, which are as Carolyn said, very expensive. So
does that cost include the shielded room?
The 1.25 million?
Yeah.
Yes, it does. Yeah. And in fairness, I should say that also it includes a very, very good shielded room. And there are, so of that cost, about 400,000 is the shielded room. And there are potentially ways to have smaller, lighter shielded rooms. So remember that the types of shielded rooms that we've been used to in MEG have to house a cryogenic system. So they have to be big. With an OPM system, you can sort of get away with something that's more the size of a phone box. So there are ways to bring down the cost of the shielded room massively, but it's still, I think, arguably the most important thing here is the cost of the sensors and making the sensors more scalable at lower cost.
Yeah, and I mean, that's from the outset, we've really been targeting a price lower than the Q-spin zero field sensors. So from a back of the envelope chat with my colleague last night, we would really hope at the moment we would project that the components in the sensor that we plan to use, that once it's a portable device, should be on the order of £1,000. Mm-hmm. And then, of course, as I mentioned, all of these things, if you can get a really good supply chain in place for lasers and cells and detection, then you can cut a lot of corners and bring the price down. But that's kind of the order of magnitude that we're targeting at the moment. Yeah.
So you can imagine that our hospital has 12, 13 acquisition systems running concurrently. So imagine, a market where, you multiply this by however many establishments you're thinking of, and you're talking a different model of business. If you think of, what we have experienced over, as I said, I started recording MEG data in Rome with the homemade system in the 80s, and there's been quite a big journey, but not in terms of the number of installations, probably not as much as they would have anticipated.
Yeah, and something that I really didn't cover, but you touched on a lot, was usability. So like user interface, and how straightforward is it for somebody who doesn't have to understand how the physics works to operate these things. So it's not something I've had to think a lot about so far, but it's something that we should really keep in mind, is making this as user friendly as possible, so that you don't necessarily have to analyze the data as you take it. You can really, as long as you understand how to operate the system. So yeah, that's something we'd really like to make as simplistic as possible.
Absolutely. And Stefano, jump in here if I'm speaking out of turn, but I think so. There's two things here. There's the actual operation of the system, but also there's the processing of the data. The data that we get are and Stefano, you sort of alluded to it. The data are incredibly rich in information, incredibly complex, and it's actually quite hard for non-experts, so people who don't have a strong mathematical background, to process the data and get to where they need to be with it. And so I think, as well as simplicity of operation of the sensors and the sensor array and the system, I think it's as important, almost more important, that there are sort of straightforward analysis pipelines that you can sort of click a button and it will tell you where the epileptic foci are.
Yeah, I think that's what I'm thinking of. Maintenance and keeping the equipment alive is another story, of course. We have experience in MRI world, and we don't have people doing it in hospital. We have companies that come in and make sure that the tuning is correct and everything is right, and that we have annual measurements of the field and the fringe field. Everything that is related to it is needed, and it's needed for any equipment. I'm more thinking, as you alluded to the idea that feature extraction is something that's very important, isn't it? So you have as much complexity in the data as you want. Think of an fMRI experiment. You can look at modulation, but do you really? Do you need to? Do you need to before you operate on a patient? Are you really interested in the interactions between left frontal and right parietal? Probably not. Is it irrelevant? No, I'm not suggesting it's not. I'm suggesting the wealth of data is there, but there are some features that are, for us, critical to evaluate. I'm running a seminar tomorrow about MEG applications and in clinical practice. And for language, if you talk to a neurosurgeon, they're not interested in the map of 95 little segments of the brain that contribute to language. They want to know, if they cut that piece, is the patient going to come out aphasic or not? And I think it's the level of complexity of data that you allow to enter in a clinical environment. It has to be agreed upon. It just can't be imposed on clinicians, but it is, I think, the work that lies ahead of any technology to become widely available.
We've just had a question about analysis. What differences would be needed to do analysis for OPMs as opposed to SQUIDs?
None. And that's one of the nice things, actually. Perhaps surprisingly, all of the, so we've had, starting from the beginning, over the last 20 years, certainly in the time that I've been working with Meg, one of the things that's really skyrocketed is what we can do with the analysis. And that's followed more or less the path of the development of more and more powerful computers. So now we've just about got computers that are powerful enough to analyze the data that we were getting probably 15 years ago on a Meg system. So that's really great. But there's been this sort of huge increase in the number of analysis techniques that we have, the power of those analysis techniques and the accuracy of those techniques. And the nice thing is that all of that literature and all of those techniques, all of the toolboxes that have been brought forward, can more or less immediately be used for OPM meg in exactly the same way as they are for squid meg. And they also immediately benefit from all of the advantages that you get from OPMs, things like the higher spatial resolution.
Thanks. I think a question for Caroline. What is the measurement range for an OPM? When does it get swamped?
So for this scheme, so this is the zero field OPMs. From the literature, I would say 100 to 150, and I believe this has been observed in the lab as well. 100 to 150 hertz is where you really get a roll off. So that's defined as kind of the bandwidth of the sensor. So the frequency range by which you can take measurements with good SNR. So we were chatting a little bit about this before this call. And there is potential for using a different measurement scheme to extend the bandwidth of the sensor. So, but yeah, at the moment it seems from 100 to 150. I haven't directly observed it because it's not a measurement we've taken yet, but we're hopeful that it will be the same for our sensor.
I wonder if the question also was referring to magnetic field strength.
Possibly, yeah. So the state-of-the-art lab-based experiments in optically pumped magnetometry can now get down to attotesla sensitivity. So, but as far as I understand, I think 15 femtotesla per root hertz is the Q-spin sensor at the moment, and that's kind of what we would be targeting in the first instance.
And what's the higher end? When does it saturate or?
So that's basically, yeah, so the field magnitude is corresponding to the Larmor frequency. And so the Larmor frequency is basically what sets this bandwidth, in the frequency, for the frequency response, if that makes sense. So, yeah, so we're talking, I think the Q-spins can tolerate maybe a couple of nanotesla, if I think I'm right. So of course, then that means you need to have a pretty well compensated field inside your shielded room, or a nice shielded room. So it would be nice to be able to live with a higher field, but yeah, you have to be quite clever to get around that.
Question from early on: will this ever be usable outside shielded rooms?
So I know the Q-spins are not going to tolerate the magnetic field of the Earth, but there have been some really interesting papers in the last year or so with unshielded MEG purely in like an outdoor environment, which is really exciting. So they use a different kind of scheme than us. It's still optically pumped magnetometry, but they're doing some kind of clever free induction decay measurements. So it's looking really promising for that. As to the signal to noise ratio, I don't know how good that is yet, but it's looking good.
Another technical question: can you use fiber optics to deliver the light to the head?
So you can, and some groups are doing this, but I think especially because this is a system where the end goal is that you could conceivably move around with the sensors on your head. Fiber optics are really sensitive to vibrational issues and also temperature. So I don't know that we would have the stability by using fiber optics. Certainly, yeah, of course you need to be connected to a computer anyway, but at the moment we haven't seen any issues in using VCSELs in terms of stability, and they certainly don't. It's just about whether we can get enough laser power is our one of our biggest concerns.
I think the question also referred to having electronics on the head and whether you could reduce the amount of electronics and possible interference if you brought the light in by fiber. But anyway, that I think that was part of the question, which I should have said at the beginning.
So the electronics. So first of all, we tried to build the electronics that we have as low noise as possible, and it's certainly not something. Noise from electronics is not something that we have yet come up against in terms of limiting our sensitivity. But it needs, yeah, we need to look at that a bit further. But as we characterize our sensitivity, we can bring the noise floor down. and or bring the signal to noise up, and then we'll see what really limits us in terms of, you know, how do we get the extra few femtotesla.
Another question about the rigid length of the sensors. Is this needed to avoid interference?
So I guess the rigid, so the, I'm not sure I understand. So is this for the Q spins or for the sensor in general? Like how?
I was just reading out the question, but I guess it refers to what was shown in the pictures.
I wonder if it's referring to the extent to which you have to hold the sensors rigidly, which is an important question. So we've recently done studies comparing an EEG cap like setup. So this is a cloth cap that you pull onto your head with all of the sensors just sort of sewn into it. And that as distinct from a helmet where you pull a helmet onto your head and the whole thing's rigid. And there is an important distinction there, which is in the cloth cap, all of the sensors can sort of wobble around relative to each other. So somehow you have to work out not only where the head is relative to the sensors, but where the sensors are relative to each other. But if you've got a rigid helmet, something more like a motorbike helmet, something you pull on, the rigidity means that you know the relative locations of the sensors extremely accurately, so through 3D printing or whatever. So you know that sensor 1 is here, sensor 2 is here, sensor 3 is here. And all you need to then find out is where the helmet is on the head. So this actually manifests as in the cloth cap, you get a random error in the sensor locations, whereas in the rigid helmet you get a systematic error. And actually the types of analysis that we do and the types of modeling that we do are much more sensitive to random than systematic error. So actually I'm not quite sure what was meant by the question, but in terms of rigidity of holding the sensors, it is very important that the sensors are held rigidly relative to each other. And so these hard helmets are much better than the sort of EEG type solutions that we've seen in the past.
Something perhaps related to that, when you have sensors close together, do they interact, and does this degrade the signal?
Yeah, that's a very good question, and something that we've sort of thought quite a lot about. So yes, they do. So if you have a sensor here and you make a measurement of magnetic field, and then you have another sensor, bring it closer and make the same measurement, you will get two different answers because the presence of the second sensor can affect the first. And the reason for that is these sensors have onboard electromagnetic coils which control the local background field. But those coils can interact with each other if the sensors are brought into close proximity. Now we do have techniques by which we can solve that in post-processing, but it would be good to get rid of that of that at source. And we do actually have a collaborative project ongoing with Strathclyde, Carolyn and colleagues, where we are trying to take their sensor design, but then develop special coils, more advanced coils, which don't have this crosstalk problem. I don't know if you want to say anything else about that, Carolyn.
That's definitely not my wheelhouse. I haven't been involved in that aspect of it, but that is something that's a huge problem for the field in general, is if you're going to have any sort of magnetic field modulation, which is really useful for the signal and for cancelling any stray fields, is that fundamentally they are going to interact. But no, that's not something I've worked on myself.
Mm-hmm.
We've got another question. Would you go for a 3-cell system like Megan Squid?
That's a good question. I guess this is relating to the Megan Squid system actually has it has triple sensor elements. So it has a system which is 2 gradiometers, 2 planar gradiometers, and a magnetometer. We wouldn't go for that specifically. but we are working in two different areas actually. So QSpin have just brought out a triaxial sensor, which we think is going to be really quite exciting. So typically in MEG, what you do is you measure the radial component of magnetic field, so the component of magnetic field going away from the head. And you measure that one because that's the largest. And it is the best one to measure. And even the triple sensor elements in the MEG-in system, they only measure field going or field gradient in the orientation away from the head. So the nice thing about OPMs is that you're not limited to just those radial measurements, so you can make tangential measurements as well. All of the QSpin sensors make dual axis measurements anyway, so we measure one tangential and one radial component of field, and the new QSpins will measure all three axes. So that's I think going to be a big step forward, and we've done lots of modeling on that and the mathematics behind it. And then I think something that's also really exciting, and Carolyn might want to talk more about this, but we're quite excited about the concurrent measurement of field and field gradient. And I think that, so that there are certain advantages to measuring field because you can look deeper into the brain, but there are equivalently advantages of measuring field gradient because you cancel out a lot of interference in that way. So so if you could measure both simultaneously, you get the best of both worlds. And I completely defer to Caroline on how you do that because I have no idea.
I mean, fundamentally, it comes down to using two cells instead of one. And unfortunately, though, the engineering is a little bit more complicated than that. So if you have two measurements, if you have two measurements in different locations, but with the same background noise, as you said, you get this common mode noise cancellation. So anything that is common to both sensors can be cancelled, and you can really improve your noise floor, the noise floor of the sensor. We have built gradiometers in the lab where we can measure, the difference in the magnetic field over a few centimeters, say, which gives you the field gradient. So how the field is changing over that distance. But we have not yet, we've not yet implemented that in the zero field system. But we have a few ideas of how to go about that. Yeah, it's tricky. Like all of these things, fitting everything inside a tiny sensor is just, we're gonna have a lot of work to do.
Well, bear in mind that if it was easy, anyone could do it.
Yeah, exactly. Good point.
Another question, is there a role for NV diamond magnetometers in MEG?
That's a great question. I'd like to think so. I'm not an expert in NV diamond, somebody else might be, but my understanding of them, my lack of understanding of them maybe, is that the noise floor is about, I think it's about an order of magnitude away from where it would need to be and I'm sort of looking, and Carolyn was nodding, which is giving me confidence to carry on. I think it's about an order of magnitude away from where we need to be to make measurements, but it is coming down. And so, I think it's not quite there yet, but hopefully that might be a competitor to OPMs maybe in a few years.
Yeah, I've seen some really promising results where people are starting to put NV center diamond magnetometers on endoscopes, and that's really interesting for clinical applications. But yeah, the signal to noise at the moment, I think, is not quite there when it comes to brain signals. But yeah, it's certainly really exciting, especially because you can embed these nanodiamonds in all sorts of things. So there's a lot of interesting science coming out there, but I don't think they're there yet in terms of the brain, the magnitude of the field from the brain.
Another question is, which I think means, is it possible to simultaneously measure electric fields, electric power, as the question puts it?
I think probably the question there is it possible to measure EEG and MEG combined?
Yeah.
And the answer is absolutely yes. We've done it. We've done it with squid systems. It's actually quite tricky with squid systems. We've done it with our OPM system as well. Perhaps bringing Stefano in on this. My question has always been, so we did this with our OPM system, right? And it took an hour to put the EEG cap on. Now that's me putting an EEG cap on, and I'm rubbish at it, okay? But it took an hour to put an EEG cap on, and then 2 minutes to put the OPM helmet on. So my question to Stefano maybe is, yes, you can do it. Would you ever want to?
So that's a good question, actually. So my answer is very straightforward. The answer is no. And the answer is no because, well, we've never done it. We're probably one of the few people that have had access to both, but never actually used it. There's literature, of course. I think that our audience is probably referring to papers that have shown that there is some non-redundant information between the two. That's not deniable. There's data that have been using, again, either somatosensory responses, so something that's got a very high signal to noise where averaging has been done, or spikes, a similar situation, and have shown that if you incorporate the two into the modeling, so you build a model in doing your either spatial filtering or inverse solution using both at the same time, with the caveat of how to do that, and you do it properly, there is some gain to be made. Very modest, but there is. The reality is that the world is imperfect. So one thing is a study on a healthy volunteer who's prepared to stay for 2 hours sitting on a, and one thing is showing you one of our kids that I've put in that picture, and imagine, keeping them still for your first half 45 minutes when you're putting the cap on. An experienced person probably take about 35 minutes, not an hour, but kids don't like being manipulated. You have to improve the conductivity by, clearing the scalp, removing greasy, oily, material from the scalp surface. Then you scratch. It's really not fun at all. And so in our MEG experience over, I've been at Aston and the Children's Hospital in Birmingham for the last sort of 20 odd years, and we've never really gone that way. We have pristine, in fact, we probably could sell them for as new 64 channel amplifiers for our MEG system that have never really been lit up. We have caps and everything. For that reason, when you start looking at clinical application, the reason why you're using MEG is to run away from that mess. And
being slightly provocative, Stefano, how should I put it? A progressive medic who has obviously embraced new technology. I've always wondered whether perhaps quite rightly, I think the field of medicine is somewhat conservative, and if you have a neurologist who is used to seeing their EEG signal from whatever sensor or whatever, are they really going to immediately give that up for this new technology that is a little bit unproven? They've not seen it before. So I guess the other part of my question would be for people unlike yourself and the Aston team who are perhaps not used to seeing MEG, is there an advantage in having a concurrent MEG EEG system, current OPM MEG EEG system, as a sort of transition from EEG into what we hope will be the more routine use of MEG?
Only if you're restricting yourself to advanced use, for example, pre-surgical evaluation of patients with epilepsy, in which case the time you spend is actually justified, and you're not looking at routine recordings about patient activity. Outpatient activity is a time critical activity to make it financially viable, you have to keep a certain throughput.
Yeah.
And I can't imagine it being going through that. The caps were seen as a way to save time, not as a way to increase your spatial sampling when they started coming out in the 80s or early 90s, and they were abandoned. And, in many places, not many places use them because the time saving is minimal. And so, yes, you're right. The medical field is a very conservative one. But the main focus needs to be on how can I transform that wealth of data into something that's manageable, not necessarily have a side-by-side comparison. It's if transition needs to be made, then of course, yes, the answer of what you're saying is yes. But I suspect that that would limit the availability of that technology to the application that I'm thinking of, maybe jumping too many steps at once, but certainly is where I see the technology going.
Can I just ask one final question in the last 2 minutes, and that is, what does the IP landscape look like? I guess this is hinting at where is the exploitation route for the UK?
I can start off on that, and so it's a not uncomplicated picture, but I think we have to look at the IP to the various different parts of this. So clearly, if we just look at OPM sensors themselves, a lot of IP rests in Colorado with the Q-spin guys, and let Carolyn talk in a minute, but right at the minute, if you want to buy an OPM, they're the only guys that you can go to. So that's the OPM. Outside that, in terms of if you like UK.plc, where might we, as in the UK, fit into this? I think there is a very positive picture, actually. So if we look at the field control aspect, so you need two things for the field control. You need electromagnetic coils, and you need shielded rooms. So the passive shielding is actually the best passive shielding in the world is being developed in Kent by a company called Magnetic Shields Limited. They don't just work for Meg; they do magnetic shielding for lots and lots and lots of different devices. But Magnetic Shield MSL are really a long way ahead of the game when it comes to making these large magnetically shielded rooms for Meg and other applications. I think the electromagnetic coils is something that we've been able to develop in Nottingham, and I think building on our experience from developing MRI scanners, we've been able to, well, I say we, Richard Botel and Niall Holmes have really been able to make quite unique systems for very high fidelity control of the magnetic field environment. So that's IP that rests with us. We have now set up a spin out company called Circa Magnetics Limited that are looking to sell this technology, and we also have sort of a patent on the way in which you put together multiple OPMs to design an array of OPMs. So we're rather hopeful that the UK can play a big role in this, but I think it would be great to have a UK-based supply chain of OPMs, and I'm not sure, Carolyn, what the plans are up in Strathclyde for that.
Well, the plans. Do you mean the plans for IP or the plans for sensors?
I guess IP, but either or.
I'm quite lucky that my higher ups keep all these details well above my head. So as far as our plans for IP, I'm not certain, but I know that a lot of the patents that are in place for the Q-spins are really to do with the sensor, the configuration of the laser, the cell, and the detector. And we're really going down a different route from them, and our readout is different. We're even using a different atomic species. So I do think that we're, for our own reasons, we're going a significantly different direction. So I don't envision any major clashes there. And as far as the steps we've taken, I'm not 100% sure.
We're out of time now, and I'll just mention briefly, I believe there is another Innovate UK competition funding call coming out early in the new year for quantum, worth keeping an eye open for that. There are a few questions unanswered. There are some that look like they're probably better handled by putting questioner and presenter in direct contact with each other. So I'll look to do that after the event. But can I just say thank you to our presenters for giving up your time and for such interesting and thought-provoking presentations, as you can tell by the volume of questions. So thank you all very much, and thanks to our audience.
Thank you.